with semiconductors. And this semiconductors thing, I don't want it to take the whole hour because how many of you want to present today? 1, 2, 3, and maybe 4. Cosmo, do it today. Do it today, Cosmo. It's like a Band-Aid. Take it off fast.
Reversible helps.
Take it off fast, right? All right, so this is recording now. Let's talk about semiconductors. So I told you, right? If we think about it, the density of states, now a view from density of states, this would be energy. And this is our density of states. We use different letters for density of states. Let's use N. It could be nu. I don't remember what letter we used in the homework. But usually, if a material is a bulk material, it might have a density of state that goes like this. For this type of material, this is the density of states here. The density is 0, but then at a particular energy, it goes up like that. So let's say it goes up like that. That's one example of what could happen with a material, right? At this point, if you look at this density of state, maybe here is the Fermi level. So at 0 temperature, all of these states are filled. That makes sense, right? It's just, I don't think you guys have seen it as a plot like this. Maybe you saw it as a plot like this, but it's in your book. So now the idea is that if it was like that, when you get to this, if you look at the energy here, and you have something happen to this guy, maybe light shines on it. If light shines on it, that light scatters off one of the electrons in there, it gives energy to the electron, right? So if it gives energy to the electron, it could jump over here and you can have a density state right here. So it could be something that is now a little bit of density here. And then you have this guy. And this difference in energy is the energy that was given by the light. So for instance, if it's visible light, it could be 300 nanometers light, right? That would be like 1 point something electron volts difference. There's other things that can give you energy. Vibrations on the lattice, those are phonons. A phonon can make it so that the electron picks up a phonon, absorbs the energy of the phonon, and then it will have an increase in energy. Okay, make sense? So if we have metals, this is kind of like the picture that we would have of the metal, that there's all of this possibility of energy states, energy, at all of these energies, there's available states. So we can go at any of those values. But then we could also have a semiconductor, and this is a picture of what this might look like for a semiconductor. So this is our energy again. And now a semiconductor might be something that looks like this, where there's a band right there, and then there's a band right here. At 0 temperature, this could be the Fermi level. But you see that all of these states are filled at 0 temperature, and all of these states over here are empty. So in this picture, we have that the Fermi level is the energy between the two bands. That's by definition. That's how it's given. Convention, people do this. But basically, there's a particular energy level where nobody is allowed to be. That's called a band gap. So this would be the case in a semiconductor. So in this case, for a semiconductor, if light were to come in, this light, right, comes in and it hits this, one of these guys. In order for it to poop it from here and pop it over here, it has to have that much energy. So X-rays have energy to move almost everything because those have electron volts energy, X-rays. Visible light, UV light might not be enough to kick you from here all the way to here. If you have a semiconductor, visible light is good enough most of the time. That's the definition of semiconductor, 1 to 2 electron volts. So this is one picture. So now another picture would be that we might get an electron. Let me just draw it on the same. So now this one, you might think that is, all right, so this is, here, we assume that this was a metal. We drew it for a metal. And in this metal, spin ups and spin downs are exactly the same. But now I could have a material that is magnetic. And what that means is that it's different. The energy of the system is different if you're spin up or spin down. So for magnetic systems, you may get something that looks like this and like this. Okay? Does that make sense? So now for a metal that is like this, a ferromagnetic metal, let's say that this is the Fermi level. So all of these states are occupied at 0 temperature. Here, there's a few states compared to here. So if you look at this blue on the left, the blue on the left is, let's say, the spin downs, and then there's more spins up. So you can see that this little bit versus all of this. So there's an imbalance of spin up electrons. Make sense? So a magnetic system would have that the two curves are not aligned the same. And this is a cartoon version of it, but it can happen. So this would be maybe a ferromagnetic system. Now, we could even go farther than this and have a system where this gets pushed up even more, or basically the Fermi energy is down here. So we could have something that has that same idea, up, energy, down. Now, this one looks like this. These are cartoons. They don't really have to look like that, parabolas or anything like that. And then let's say your Fermi level was here. So that means that everything here is occupied up to this level, but then you see that this spin down density is gonna be 0 because there's no spin downs. So what happens there at this particular Fermi level, and the Fermi level doesn't have to be near this spin down curve. It could be even lower, right? What we see then is that there's no spin down in this material. So this one we actually find a lot in nature, ferromagnetic. We have ferromagnetic, antiferromagnetic systems, all kinds of stuff, right? But this one is actually not as available, but there are materials that do this. So for instance, chromium oxide is like this, and they're called half metals. So this is a new, I don't know how new it is actually, but it's a conductor for spin up systems and is an insulator for spin downs. Questions about all this?
Do these half metals typically happen in like the higher level or the higher order metals like lead or bismuth typically, or?
No, it can be just because that's the band structure that they take. So this takes place in chromium oxide, for instance. You can do things with palladium, but I'm not, I don't think that there's a rule that says this is the one that would work. All right, so a little bit more about semiconductors. So you guys know semiconductors are important for electronics, right? But what do we use before semiconductors? You guys have seen this maybe in your grandpa's house. All radios have those.
I do recall a lot about vacuum tubes.
Vacuum tubes. So a vacuum tube is a cathode ray. Vacuum tubes were rectifying current. They were doing different things. That's what the vacuum tube is for. So how many of you play music? All right, you guys have electric?
My father.
You guys have amplifiers? What kind of amplifier do you have?
Like one for a guitar, one with the
Solid state or vacuum? Or vacuum tube? How about you?
I think my father.
How about you?
My
You don't know?
father's is both.
Both? Okay.
Semiconductor and
So vacuum tubes still exist in sound systems. Why? Because vacuum tubes are amazing at the sound that they make. So they're processing the signal. And actually we can mimic all of that with semiconductors, but semiconductors are so perfect compared to the vacuum tubes, right? That they sound weird. It's artificial. So when you have distortion pedals, when you in guitars or things like that, you have all of these components, electronic components. They're full of maybe transistors and things like that. But there's really expensive amplifiers that still have the vacuum tubes. And if you break a vacuum tube, they're like $100. So that's the reason. So cathode rays or vacuum tubes were where modern electronics was started. But electronics is with vacuum tubes. That's when we start doing electronic stuff, radios, things like that. I would say that information technology had to happen once semiconductors were ready. I mean, there were a few vacuum tube supercomputers that were probably less powerful than a calculator, but people were using them before semiconductors were mainstream. But they were the size of buildings, right? They were using them with mechanical calculators, vacuum tube calculators, all of those. They would call them then computers, but they were not what we would use as a computer. So semiconductors started around 1874. There were two fellows, Brown and Schuster. And what happened is that Brown was using crystals of ferrous sulfide. And then he started looking at the resistance as a function of where the current was flowing. If you have current flowing in this direction, he noticed that it was different than current in that direction. And the reason for that is that if you look at current as a function of voltage, for semiconductors, that could go like this. This is very different than for normal ohmic materials, where there's something that goes like that. And that slope is the resistance, right? And I is equal to B times R. No, wait, B is equal to I times R, right? So that's the slope of this curve. So when they did this, they noticed that it was something like this, and it would be different if you put the 1 volt in this direction. Let's say 1 volt was around here. The current was different than if you put the 1 volt in this direction, negative 1 volt. And they were measuring how much current they were getting. Also, there's a picture of the first transistor. It was developed during the 30s and 40s. And what they did is that they had chunk of germanium, and it has two terminals like this, and the last terminal is like a big rod that was brought in on top. And actually it would behave different depending on where you were putting the rod, and they would have to move it to make it do the right thing. So that was the first transistor that was invented in Bell Labs. And the reason for that is that they had to make them big. They have a lot of impurities, and impurities change your system completely. So if you look at a system that has 10 to the 10 electrons, that's what in per centimeter cube. That's the number of electrons that these guys have, 10 to the 10 in a centimeter cube. If you look at gold, it has 10 to the 23 or so atoms in a centimeter cube. And it might have 10 to the 23 or more electrons traveling in 1 centimeter cube. These guys are just 10 to the 10. So it's not 10 to the 23, it's a huge magnitude difference. So if you have impurities in there, those impurities, usually you measure how many impurities you have as parts per million, maybe parts per billion, right? But you see that a part per million means that there's thousands more atoms that are not supposed to be there. That's your impurities. So you have to make atoms. You will have to make, if you have an impurity per 10 to the 10 atoms, so 0.1 impurities for each billion atom, 1 per 10 billion, you already are changing the electrical properties of the system, and it's not the same semiconductor you started with. So that's really important, and that's what makes it different, that you can do things with them. What else? Yeah, so we have talked about the experimental, the systems, like these things right here. This is density of states as a function of energy. And then I also gave you, let me put this picture here. So this is silicon. I think this is the picture from your book, right? I took it from your book. So you have here energy, and then here you have the directions in momentum space. So gamma is the 0, 0 direction. And then this is in one direction, maybe it's kx, maybe ky, and this is in another direction. I guess this is kx and this is ky, one of the other ones. So if you have silicon, you have 1, 2, 3, 4, 5 bands presented here that are important. Here is the top of the valence band. That's where holes like to be. And at 0 temperature, here is the Fermi level, halfway between this point and this point. So at 0 temperature, there's full of electrons here. All of this is full of electrons. And then as you increase the temperature, electrons could start going in this direction. So if you have enough high temperature, that might be like 1,000 electrons over here. And if you have 1,000 electrons here, you're left with 1,000 holes down here. So the holes can also conduct electricity. You can think of a hole as a bubble, and the bubble moves around. It's not that the bubble is moving, right? It's that the fluid is coming up, and that's what it looks like. The cavity is moving. The hole is just like that. So that's for silicon. And something that is important here is that your momentum shows you here, this is at 0, 0, 0. An electron here, if it gets hit by light, wants to go, and it could find a state over here, wants to go from here. If you give it enough energy, this much energy, it would say, oh, I'm here. You just gave it that energy. I'm here, but I want to be over here. So it has to get a kick in momentum. Light is massless, so it doesn't have that much momentum. Does that make sense? So what has momentum? Other atoms. So if an ion bumps into you, it gives you the momentum that you need. And an ion or atom can bump into you when the ion is moving. And if you're at 0 temperature, there's not that many motion of the ions. But if you're at higher temperature, there's enough ions moving back and forth that you can absorb energy and momentum from there to jump over here from the light and then get kicked over here by the momentum that the atom gives you. Collisions with ions and atoms doesn't give you that much energy. So they're mostly like tiny little, in this scale, it would be tiny little energy differences. So you wouldn't be able to just go from here to here without the light giving you a lot of energy. So light gives you a lot of energy. But now no momentum actually. So this makes silicon an indirect semiconductor because it's indirect transitions that happen. You have to go from here to here. We can compare it with germanium. This is germanium right here. And you can see that there's 2 points that are interesting. All right, I don't want it to do that. Let me fix this. Ah. All right, so this is germanium, right? The difference here is that, again, you have 1, 2, 3, 4, 5, 6, maybe even 7 bands that are important. But the most important are these 3 right here. And if you look at it, the energy to go from here to here and the energy to go from here to here are close enough. So now light, visible light, could bump you from here to here, and if you get light, it can bump you from here to here if you couple that with a momentum kick. So for this system, germanium, it's a lot easier to have those transitions. If you compare it with this system, right? This energy difference from here to here is about 3 electron volts. Here is about maybe 1 point something electron volts. Maybe it's 1.1 and 1.2 electron volts. So there's light that can take you up here. So germanium is a better semiconductor for these optical transitions. Cosmo, you had a question?
Yes, I was actually wanting to ask, why does the optical transitions between silicon and germanium differ so much, considering they both belong to the same
right.
atomic group?
They're almost the same, except how their electrons are arranged. The arrangement of the electron is shown, well, I guess not in this picture. We actually have the Fermi wave vector. Anybody have, no, sorry, the Brillouin. Anybody have their books with you? If I can borrow the book, I can show you the image in another, I have it right here. All right, I can show you the different images. Is in, I believe, chapter 3. When you look at this, guys, so this is the same picture as in your, this is your book, right? So this is the same picture I was showing you before, where there's a difference from here to here. So it's the same picture I was showing you, but now this one is next to this picture. So this is the Brillouin zone. This point right here is the gamma point. So this gamma point is where the holes like to be. But here they're giving you these ovals, which is where the electrons like to live. And they like to live over here by the X direction. So this is actually the X direction right here. So you see that this ball right here is actually this little ball right here. So electrons like to be over here in that momentum region of space. So that's for silicon. This is the same picture I just showed you, but electrons like to live over here. No, wait, over here. Not up here, right? But on the opposite direction. So this is L. So you see L is the one going in this direction. X was the one going in this direction. So they're not in a little bulb right here, but they're actually little bulbs right here in this facet. The L's go with the hexagons. The X's go with the squares. And this is the first Brillouin zone of the FCC lattice. This is the momentum representation of the FCC lattice. So this unit cell right here, this bulb right here becomes half of this guy right here. And then there's this periodic, so there's another half ball on the other ones next to it. So that's why they're so different. And then this brings me to the last one. I can just put it here for you guys. This is gallium arsenide. And actually this one is even better because it doesn't compete with these guys over here that are too high in energy. This is the best one for it. So it goes from here to here directly. So this is a direct semiconductor, whereas these two guys are indirect. Although this one can also populate things over here. So once we look at this one, this is a direct transition. You don't need a phonon to move you. You don't need to hit an atom to move you up and down. You just need the energy from your photon. Light comes in, bumps you up. So this guy, the electrons live right here in the gamma point, right in the center. So that's something that you calculate quantum mechanically with whatever theory you like to do. And then the question is, how would you measure it? So I know we're not yet in techniques, but I need to tell you exactly what this technique is doing, I think, before we start with how the other materials behave. So we have band structure. This is what I was showing you right now. So the picture was like gamma in this direction, X in this direction, and I think L. So this picture has the momentum. So energy is up. Then this down here is your momentum, right? Except, so this is 0, 0, 0. Let's call this one 1, 0, 0. And this one could be 0, 1, 0. It's not XYZ, but it's actually the basis in the FCC lattice, which is what silicon and germanium use. And if we look at those, let me draw this guy. We would have holes right here. So these two lines are holes. And then over here, we have the conduction electrons. They like to be there. There's another band that goes like this, and then there's another band that goes like this. So those are the electron bands. All right. No questions about this yet, right? Same as before. The other picture that I gave you is this cartoons, right? So how does it work for this one here? Well, actually for this one, I could have the same picture. This is the energy in this direction. And then here, I'm gonna be plotting the number of electrons, my density of states. So this is density of states. Again, this could be N, nu. We use so many letters, I forget. So I also teach the semiconductor physics class. That's an undergraduate class sometimes. I don't know if any of you had to take it before. It's actually for the electrical engineers mostly. We stopped teaching it that often, but it turns out that we just discuss semiconductors for the whole semester. And every thing in there has an N. All of the symbols are N. So it gets really confusing. This is just an overview. If you want to learn a lot more about semiconductors, we can do that. So there's some features that carry over. Like for instance, this is the same energy as this one. So this is like that. Then because of this too, this is what the density of states would look like. We will have how many states are at particular energy. So if I graph and start integrating in this direction, I'm gonna get a plot right here. And it's actually a plot that looks like this. So there's that one for those guys. Then there's a gap, and then is maybe like this. And maybe I'm exaggerating, but this one is kind of smallish up to here, from here to here. And then it grows big because now you have to introduce all of these guys when you start integrating them. So this is your density of states. This is your band structure, your density of states. And then to that, we can add the Fermi-Dirac distribution. Fermi-Dirac as a function of temperature and energy. I forget the energy, energy goes here. So that's the one that, and this is again, the same line over here coming across, right? This one is gonna be like this, where is 1 or 0. Oh, 1 or 0. This is T is equal to 0. So if you want to figure out if there's electrons here, at T is equal to 0, there's a lot of electrons. If there's electrons here at T is equal to 0, there's none, because you would multiply these two together and you see that here is 0, doesn't matter what this is. But then if you start going to higher and higher temperatures, you would have that this starts growing a tail like this. So you would go like this. And then it follows this line. So maybe this is at 295 Kelvin. This is at 0 Kelvin versus 295. And now here at this energy, you multiply the density of states with whatever value you have up here. And now you can see that there's electrons that can be occupied and some energy values here. Any questions? So Fermi-Dirac distribution is important. Density of states is important. And band structure is important. They're telling us, these two guys, whether electrons live at a particular energy. And then this guy is telling us whether an electron lives at a particular energy and momentum. This one tells us how many electrons in that area. This one tells us the same thing, but not just for electrons, but also for, not just for energies, but for momentum. All right, so now how do you measure this? How many of you know an XPS machine? No, not the computer, a machine, an equipment that we have in the department. You're calculating binding energies, right? So we have XPS is X-ray photoelectron spectroscopy. You're sitting exactly below it, except it's 5 floors up in Dave's lab. Well, I don't know if this is below Dave's lab. Let's assume it is. It's not below Derek's lab, right? Are you sure? All right, so just move a little bit that way, and maybe in the hallway, that's where McElroy's lab is. In Dave's lab, they have a way to send X-rays and probe an electron from down here all the way out. So they've sent a lot of energy, photons, and then they can get, there's electrons there, boom. And we know how much energy they have. They calculate how much energy it took to separate it from being down here. That's what the XPS is doing. But actually they can tune it and not use X-rays, but they can use UV light. So instead of being in the -10 electron volts, the electron could be living here or here or here. And then they send the light in. And when they send the light in, they have a detector that detects that an electron got kicked out. And they pick it up. So in the UV is UV So the other one was X-rays, is XPS. In the UV, it's called UPS. And Dave has that capability. So Dave can kind of tell you what this picture looks like. Now, what he's doing is that he's taking all of those angles that the electron can be coming from, all of the momentum, if the electron is traveling in that direction or in that direction, he measures them both. You can make another device or use the same device, but then put an angle selector. And now you figure out that electron that I just grabbed from the material and pulled out with the X-ray or the proton or the ultraviolet light, what momentum does it have? And you start plotting these guys. And you get this band structure information with a material that is, for that material, with an equipment that has the different selectivity that the detector can move or something like that. So that one is called ARPES. So we have XPS and UPS can do this kind of setup, X-ray photoelectron spectroscopy. And then this one is called ARPES, which is angle resolved photoelectron spectroscopy. So this ARPES, we don't have it here. Maybe Dave could do it if he had the patience to do it. But it can actually be done with, so the limitation is how much time you want to do it, right? They actually have super bright X-ray sources in national labs, and then they do this kind of measurement. So Argonne National Lab, Berkeley has facilities to do this super fast. The XPS up above, I don't know if you can do it unless you had a grad student that wants to stay hours and hours trying to take those measurements. Questions? No? Yeah? Uh-huh. Uh-huh. So I'm not sure if I understand your question completely. Let me see if I can rephrase it. Right, so for instance, there's an electron right here. But when if you remove it through an X-ray from any of these bands, but let's just assume it's down here, then we would see that a bunch of them are coming around that 0, 0, 0 momentum. So they don't have any momentum. So that means that they're just not moving too much. But if you remove it from this other end, you're gonna see that electrons are coming in mostly from one direction. Or they're traveling and they have this much momentum in them. So that's what the direction selectivity is gonna be coming in, that you can select, they're coming with a different angle. They're not coming, you send the light in and then electron is popping out with 0 momentum change, but actually you see that they have a different angle they like to pop up. And that's the angle that tells you what direction they like to travel. And this is velocity, momentum, right? But it's kind of like velocity. So they like to travel in this direction mostly and not in this direction. So that's what your selectivity gives you with this angle resolved. Does that answer your question? All right, Cosmo?
Yeah, actually, I did encounter a little bit of this when I was in Dr. Rosenberg's class last semester. One of the things that I didn't quite understand clearly at the time was on those, in the band structure, they mentioned that the lower end is supposed to be for the valence holes, right? Well, during that, we were introduced to the concept of light and heavy holes. I was kind of wanting to understand a little bit more clearly as to how those are selected
All right.
typically is favored in transition over.
All right. So you sure that you're not asking that question because you don't want to go and
I'm
present, right?
also actually genuinely triggered.
All right. No, this is a good point. So we have holes right here. So let me cover this, which I wasn't intending to cover yet. So I wanted you guys to present. But Cosmo brings up something that I can point out really fast here. So this is right here. Energy as a function of momentum K, right? This right here, this guys. There's several of them. So the red ones, the momentum is over here where it's parabolic. These guys are parabolic right here where momentum is 0, these two guys. But there's a difference between the two. So if I wanted to grab this energy for the electrons in the valence band, I would have to figure out what is the valence band value. So this is my valence band right here. That's the number that would go there. And then this is a parabola more or less. We can assume it's a parabola at least around here, right? So then we have a parabola and this one goes, there's an h square, there's a 2. And then here we would have a matrix. Well, actually it's a tensor that depends on this, that gets multiplied with this vector. So we have a quadratic equation. So this is a tensor. You guys are familiar with tensors? The word tensor, it's just a matrix, right?
Matrix of a matrix.
In this case, it's just actually, so this is the mass tensor. In this case, it's just a matrix. And then if we were looking for this guys up here, so this is for the holes. For the electrons, I would have that my energy, you guys can still see this part. My energy as a function of momentum is given by some value of this energy right here, and then a parabola. This is the conduction band, and then the parabola faces up, right? So this parabola has the plus h squared over 2. Then we're gonna have two vectors, one here, then this inverse of the mass tensor. I put, because vectors have a line, an arrow at the top. Tensors are usually a big bold matrix, but it's hard to make bold when you're writing in a piece of paper. So I put 2 lines under it. And that's your tensor in the bottom too. So basically this effective mass tensor, we have the conduction band and what we want to do is fit these guys to that particular value. So let's say we had something very simple. It's gonna look like this, and then like this, and then the red one is gonna be somewhere in between the two, like this. So now we have energy here, and we have the K value, right, in that direction. So if I wanted to do the red ones, I figure out what this value is right here. And this distance from here to here is my conduction band, the value of the energy there. So this is the conduction band. And it's gonna be whatever this guy is at the bottom, plus, and then in this case, how do I fit this parabola, right? So it actually has h bar k squared over 2, and then some number that I don't know. In this case, let's say that is symmetric. So this tensor inverse would be mass in the x direction, mass in the y direction, mass in the z direction. And then the other entries could be 0. Does that make sense? Because it's symmetric, it's a very simple tensor. So this is the mass of the electron, and this actually is symmetric. It would be actually the 3 are the same. So this equation that looks very complicated is just the k square comes out of here. And then they multiply this mass tensor, which is actually the inverse of the masses. So if we look at the bottom ones, we would have the same thing, right? It's with the minus sign. But then the only thing that changes, I'm not going to change the k value. Let's say I'm at a particular energy, right? I'm not going to change the only thing that can change is what this parabola is. So if we look at this one for the heavy holes, is equal to this valence band minus h bar square, k square over 2. And then there's some value that goes here. And then for the light holes, it's another value. So the question would be, and it's exactly the same, the only thing that changes is here. The question becomes, if this is symmetric, they're all the same in this direction, but which one is the heavy one and which one is the light? So this basically this tensor right here is the inverse of the mass. It's actually telling us the inverse of mass is telling us how much this is opening up by. So this is the curvature of this thing. If we wanted to plot basically, this is going to be EV minus A h bar square k square over 2. If A was 0, we get a flat line, right? At EC, at EB. If A is big, I get this guy. So if A is B, I get this guy. If A is medium, I get this guy. So now this A is the same as the inverse of this. So we can say that this is 1 over mass. So which one would be heavier? The one that has more curvature or the one that has less curvature? Less or more?
As it goes to 0, it's going to go to a flat line, right?
Right.
So then
And the flat line means that the mass is 1 over 0.
1 over 0, okay.
So flat band means that it's very massive. Very compressed band, very bent, is light. So this becomes the light hole, this becomes the heavy hole. And I actually never remember which one is which. So I always have to think in my head like that. Which one would be the massive one? And it's not until you do it like 10 times that it gets into your brain. So if you have a very flat band, that means that it's a very massive type of electron. Okay? So that's where the light holes, heavy holes come from, Cosmo. And in this case, this is gallium arsenide, which is what I'm modeling here. With those parabolas, they will look like this. All right, so enough about semiconductors. I think we covered enough. You can grab a semiconductor band structure and get all of this information out of that. Who wants to present your materials now? Do you wanna go first? Go for it. You're doing PowerPoint, right? All right, so do you need to sign through Google Chrome?
Yeah, they have Outlook on Outlook.
Ooh, I'm not sure.
Probably get the Outlook through Chrome, maybe?
All right, try it. Is anybody missing? All right. Let me just share the screen now.
Okay.
Hold on, okay?
Yeah.
Give me 1 second. So share, stop video here. Share screen, and we're sharing the screen just like that. And I hate this thing. Let's put this on the bottom. There you go. Hopefully it works.
Yeah.
So calculating band structures, that's something we do for all new materials. Everybody would be getting all of this information now of a new material. And if you make a new material, then you go and measure its band structure. For most materials, that gives you a lot of information. So if you look at McElroy's, Jost, or Myers group, I think that they all get that kind of information from the band structures. All right, so the floor is yours. Hold on, let me put this in.
Okay. Yeah. Okay, so I'm presenting on copper, indium, gallium selenide, which, like I said, is what I do some of my own research on as a part of Dr. Brenda's group. So from here on out, I'm gonna be calling it SIGS, which is just a shorthand, and it's obviously way easier to say. So what is it? It's actually really interesting. We've just been talking about semiconductors. SIGS is a really important semiconductor. And so as we know, as the temperature increases, its resistivity is going to decrease. And it has a really interesting chemical structure, which I had never actually seen something like this before until I started working with SIGS. So it has copper, and then you have indium, and it appears as 1 minus X, and then gallium appears as X, and then you have selenium. You always have 2 selenium no matter what. And X is going to have the value of either 0 or 1. So when X equals 0, the material exists as pure copper indium selenide. Yeah.
You can go from 0 to 1.
Yeah.
Not 0 or 1. You can go in between two, like fractions.
Okay. Yeah. Yeah. That's what. Yes. Right. So it can go from 0 to 1. So when it is at 0, you have just pure copper indium selenide, right? Because at 0, you get that there's no gallium in it, and you just have 1 indium. So, like Dr. Bruna said, you can increase the amount of gallium in there, and you have a mix of both of them. And so when you actually have a mix of both of them, the material can be classified as something called as a solid solution, which is something I never heard about again until this. Basically, you can have that, you have these 2 materials, the CIS, the copper indium selenide, and then the copper gallium selenide, which is when X equals 1. They can kind of exist together, but it doesn't change the crystal structure. So I'll talk about that in just a minute as well and actually show what it looks like. But yeah, super cool material. And this just in the chemical formula, I think. So this is what it actually looks like. This is the unit cell for SIGS. So the blue atoms here represent the indium / gallium. And so what I was trying to say about the solid solution is that you can have that, say this blue atom here is gallium, and then this blue atom here is indium. They can exist kind of at the same time in the structure without actually altering how the crystal itself looks. So the blue atoms are the indium gallium, the red atoms represent the copper, and the yellow atoms are the selenium. And as we kind of talked about before about crystal classification, SIGS falls under the tetragonal crystal. Yeah, Cosmo. Okay, yeah. So it falls under the tetragonal crystal classification. It's technically tetragonal body-centered with 16 atoms in the unit cell, which is not necessarily shown here. So it also exhibits a lot of tetrahedral bonding. Each one of these atoms has 4 bonds on it. So these red copper atoms, every single one is going to be bonded to 4 selenium atoms. And so if we were to repeat the unit cell, you'd see that over and over again that these red copper atoms are always bonded to 4 seleniums. And then each one of these yellow seleniums is always going to be bonded to 2 either gallium or indiums and 2 coppers. So each one of these atoms has 4 atoms bonded to it. Yeah.
All right. So pulling back just on just building off of what you said.
Yeah.
So is this X value that's in the chemical equation for 6 related to the ratio between indium and gallium?
Yeah, that's pretty much what it's telling you, is that, like Dr. Brunda said, that I didn't put in the PowerPoint, is that it goes from 0 to 1. It's not just 0 or 1. So when you're increasing from 0 to 1, you're altering how much gallium you're adding into it from pure copper indium selenide. So yeah, you can have a mix in there, and that's what that X value is basically telling you. Okay, so properties, a lot of the properties I'm going to talk about are actually about the band gap, which we talked about today and Tuesday. So it has a variable tunable band gap. So when you start with pure copper indium selenide, CIS, the band gap is measured to be about 1.04 eV, which falls under the semiconductor spectrum we saw. And as you begin to add gallium into the system and you start to change that ratio of indium to gallium, the band gap actually starts to increase, and it increases all the way up to 1.7. So when you have replaced all the indium in the system by gallium, you've brought the band gap up all the way to 1.7. But when you change the ratio, when you have a certain amount of indium and a certain amount of gallium, you can actually change to band gap values in between 1.04 and 1.7. So it's tunable is kind of what it's called. And that's going to be really important in just a minute. And so then, okay, so this is kind of what we were just talking about actually, is that SIGS is a direct band gap semiconductor. So basically what that means is that the peak of the valence band, like we just kind of saw, it lies at the same momentum value as the minimum of the conduction band. Okay, so this figure on the left displays a direct band gap semiconductor, and then the figure on the right is an indirect band gap semiconductor, where these minimums and maximums of the conduction and valence band occur at different momentum values. So why is that important? Well, there's a process called radiative recombination, which is, so as we just talked about, you can see that electrons can be promoted from the valence band to the conduction band to allow for electrical current to pass through that. But a process can also happen where some of these electrons that were promoted to the conduction band can actually fall back down to the valence band. And so it's called like electron hole recombination. We just saw what holes are. You leave a hole behind when you promote that electron. And so what happens is they fall back, this hole in these electrons that fall from the conduction band recombine, and you actually emit a photon. So you give off light when you do this process. Now, the inverse process that, the obvious inverse process, this would be actually absorbing light. So instead of having these electrons fall back down to the conduction valence band and emit light, you're actually absorbing light through the opposite process of, yeah. So what's important here to notice that as a direct band gap semiconductor, this process can happen a lot quicker than an indirect band gap semiconductor because you don't need a phonon in order to actually complete the process. And the phonon is needed, as we talked about, to conserve momentum in this process, because if you're not conserving momentum, obviously breaking fundamental laws of physics. So without a phonon, it's allowed to go a lot faster, and it's generally more efficient in this light absorption process. So how does this stuff apply? Obviously, a lot of this stuff could be, when you're talking about light absorption, it sounds like it's a really good candidate for some sort of photovoltaic system, and it is. So talking about the tunable band gap from earlier, you can actually tune, there's been people who've tried to tune the band gap of SIGS to match the spectrum, the solar spectrum, so that we can get even more efficient light absorption from the sun. And like I said, SIGS can absorb the light quicker because it is a direct band gap semiconductor. So you actually need less material to absorb light. Because if you have an indirect band gap semiconductor, you could have light come in and it could travel really, really deep into the material before it's actually absorbed. But with this direct band gap semiconductor as SIGS, it can just come in and it'll be absorbed really quickly. So you actually need less material for full light absorption. So like I said, this points towards SIGs being incredibly useful and cost effective, as you need less material in the production of solar cells. And so SIGs, thin film solar cells, are a really interesting and still in development kind of photovoltaic device. So they're made by depositing a super thin layer, that's why they're called thin film solar cells, of SIGs onto a substrate that is either glass, metal, or plastic usually. So this allows for the possibility of a commercial production of super flexible solar cells when they're made of plastic. They could be super thin and super flexible. You have a lot of different uses for them. And like I said, they can be made at a lower cost because you don't need as much material to absorb as much light. So compared to an industry standard silicon that's used in a lot of solar cell productions, it absorbs it way quicker, and it's not as efficient, but the cost is really appealing to a lot of engineering practices. So here's actually what it looks like when you actually build it. So you have, again, this substrate on the bottom, either glass, metal foil, or plastics. And then you have, I forget what MO actually is, but it acts, what's that? Yes, that one. And it acts basically as a it allows for conduction in the system to actually use the energy. And then you have your SIGs layer here deposited with cadmium sulfide on top of it, and that acts as a photoresistor, which just increases the process. And then you have this thin window up here that allows for the sunlight to actually come in, and this is usually made of a conductive oxide. Super commonly, it's zinc oxide that's used in this. So yeah, so that's what a thin film solar panel made of SIGs actually looks like. And then, so here's a little bit of my personal research. I just want to talk about this a little bit. Basically, what I've been doing is studying the effects of particle radiation on pure copper gallium selenide. And we've been doing this by a process or a technique known as time-dependent density functional theory. And we've been trying to calculate the electronic stopping power of this material. And that refers to the slowing down of a projectile ion traveling through the material due to a bunch of the collisions and interactions with all the electrons in the material. So here's the actual unit cell I've been working with. This is like a 2 by 2 by 2 of the base unit cell, just multiplied everything by 2. And then, so this is the actual CGS itself. And then up here, there's this little dot, that's the hydrogen. So we put the hydrogen in the system, and using that time-dependent density functional theory, we simulate this traveling through the material at a range of different speeds. And we can study how the electronic stopping power changes at these different speeds by looking at the energy of the system and the energy transfer that will come about from this radiation particle. So at a speed of 1.2 Bohrs times energy divided by h bar, which is the unit speed, you see that this is the kinetic energy of the particle as it's traveling through the material. So it's steadily decreasing, and you have kind of these points. That's going to be around where you're around probably bigger atoms or something like that. And you're going to be decreasing this energy. And if you look at the energy of the crystal itself, it's actually going to be the complete opposite, that all this energy is actually increasing in the crystal. And then so we can look at the average change of energy as a function of distance. And the distance refers to the distance of the traveling particle, how far it's actually moved at a given speed. So we can study the average change as it moves through the thing. And that's really important because that basically allows us to calculate the electronic stopping power, which results in a graph that looks something like this. So basically, you can see how much it stops as a function, how much it's able to stop a projectile ion as a function of these different velocities. So that's actually all I have about SIGs. So yeah. Yeah.
So CIS, like operator, it's pure in this pure form we find it in the nature, or we have to artificially build gallium into
Ye-
Or
I
like both of them can exist like purely in the
I think it's manufactured, and I think when you start from pure, like you said, yeah, you dope the gallium into it, and you increase it manually through. I believe that's right. I actually don't know if does it exist naturally, or it's no, yeah.
That's six. As far as I know, that's six.
Right. So yeah, from the actual production of SIGs, it's man-made.
Prepared by either chemical methods, and then when you're preparing chemical methods, you can put different constituents, right? Like
Yeah.
say that. Actually, I don't know how it's grown. Actually, we should look that up.
Yeah, I haven't looked into that.
If you have like two salts and you mix them together in some liquid, then the salts open up and then those two different things can join and make something, right? So that's like kind of like the chemistry.
are they found in like solid form or is it like in liquid or something? Like if it's in solid form, then we can mix them together by measuring their weight.
Right, so that would be like the solid state that you keep it solid, you warm them up, and then they can use it, right? So yeah, I actually don't know exactly how they're made. I just know that they can make them so that you have a gradient of those two. So maybe
Yeah.
with the solid reaction, you can see that you have that gradient. And because, like you were saying, well, the band gap changes as you can increase the band gap, right?
Mhm.
So if you put the highest band gap material on the top, then that absorbs all of the higher energy photons, but doesn't absorb this chunk of photons that can absorb a lower and lower.
Right.
By having this gradient band gap, you're absorbing way better.
Yeah.
And that's what they have made. SIGs in some SIGs have that particularly built like that so that they can absorb light.
Mhm. Yeah. Yeah. Whoever.
Go on ahead.
This is for CGS, right?
Yes, the research I've done is for CGS, yeah. No, currently we have someone else in the group who's actually looking at copper indium selenide. I've just been doing, the CGS for all my research, and basically you can combine the results of the two to get to get a good idea of SIGs as a whole when you're looking at the extremes, basically.
We do use the same technique to look at other materials.
Yeah.
So Rusty is looking at some perovskites. Perovskite is another crystal. So this is a crystal structure that SIG has a particular crystal structure. And I think it's called zeolite.
Yeah.
So that's just the name of the mineralogist that found out this structure looks like that. So it turns out that Perovsky was the head of the Russian, or before even he was Soviet, before he was the Soviet Union, he was the head of the Russian Academy of Geologists or whatever. But then archaeologists discover some material with a crystal structure and says we should name this one Perovskite in honor of a great leader. So then perovskite is another material that we're really interested in. These two are almost similar, and then it's actually, but we're doing that for the thinness of the material. So if you can make solar cells that are thin, you can, they don't weigh as much. You can send them up to space better. So you mentioned silicon.
Mm-hmm.
What is the thickness of a silicon solar cell?
It's like, I think it was like roughly 180 micrometers, or actually no, it might even be bigger than that. I don't remember, but I remember that like silicon is like a fraction of that, or the SIGs is like a fraction of that in a solar cell.
So because it's indirect band gap material, it has to be thick so that the electrons get produced, because the light has to pass through all of this material before it gets absorbed. Remember, you have to pass light and shape chromophore. Because this guy is direct, you can put a film, and thin films can be a couple of microns thickness, right? So if you're going with something that is, let's say, half a centimeter and sending it out to space, versus something that has to just be like 0.001 of a centimeter, you want to go with a 0.001. The weight is really important. When you send things to the space station, they charge you by weight.
Mhm. Yeah,
Silicon is not flexible.
right. Yeah, no, they're being manufactured. They're definitely not like the industry standard yet, but a lot of like I said, the cost effectiveness and how flexible they are is really appealing to a lot of people. And like the efficiency, like I think the highest recorded efficiency for a SIGS thin film solar is like 23.2% or something like that. It's definitely not, that is not the highest like efficiency by any means, but it's just, like I said, it's just such a promising material that it still is definitely being developed on. And it has, for like the last 20 years, it's been a lot of development into this material and engineering of these solar cells. Yeah.
One last thing. This was just something I was a little bit curious about. I noticed that at some of the very low end speeds, it seems as though the electron stopping power of the material seems to decrease.
Yeah.
I was kind of curious as to how and why that occurs, because like usually when you think of like say like a bullet analogy, usually faster means greater penetration.
Right.
But it's sort of like strange to sort of imagine like it's sort of like if you shoot. Yeah. So I was just kind of curious to see how that might be occurring.
Yeah, I mean, I'm not actually 100% sure. There's actually a couple of speeds that go further to the left, a little even slower speeds. And actually just recently we've gotten some interesting results, to say the least, that don't really follow the trend. So I think it has to do with just when you're moving slower, you're getting a lot more interaction around all these electrons. So maybe it's going to affect your speed and trajectory a little bit more. So it's a little bit harder to actually stop it because you're spending so much more time near all these electrons, all this energy can be transferred, that it's going to change how it's moving a little bit differently. So like I said, I'm working on trying to figure out exactly what's going on down here. We're having, like I said, weird results coming out of that. But yeah, that's a good question, actually.
Yeah, so that's what we're studying. And the peak corresponds to where is it that you have the trade-off before. So if you're going too fast, you don't have. And I guess if your bullet is really fast, it goes straight through the.
Right.
Yeah.
So this is telling us how much damage that projectile is. So there's a trade-off. You're going slow enough to do a lot of damage, and that's the peak.
Yeah.
Okay. All right. Yeah, I was thinking about that because yeah, usually when you change barrel lengths, that's usually when you start introducing those velocities. And depending on what kind of bullet you have, because sometimes when you go slow enough, it actually ends up depleting the damage potential.
Yeah.
So that actually does make a lot of sense.
Yeah.
And then the important thing is that we want to know this changes from materials, but it's the same change that changes a lot of speed. So what happens then is that is speed where the peak is. When it hits the same speed at which the protons from the solar wind are passing through, right? Then that's going to be really bad because these protons are going to destroy your solar cell. But if we have a material where that peak is not there, but it's moving to the left, and solar flares send protons out, but it's not going to be as damaging, then we're good. Or if the peak is over here, so the highest concentration of solar protons could be near the peak, or we could maybe do something so that they're not together. We actually are actively researching how to do that. And if you can reduce the peak to reduce the damage, but you also have to think about it. Like, for instance, if you guys were out in space and a solar flare happens, that would totally destroy your cells. DNA damage, might get cancer later.
Yeah.
All right. So anything else? We're out of time. But if you have another question you want to pose, now's the time. If not, let's get Paul again.
Yep. Yeah.
And then another you finish it, logging out, you can just putting your stuff away. That's the reason that if we go to Mars, it would be really hard because we have to have NASA has to have a way to protect astronauts. There's going to be spending months in space. And solar radiations can happen at all. I mean, there's a way to predict the climate, the solar climate, but it's not perfect. And you can have a solar flare coming up and then radiation coming at the astronauts. So you need materials that can stop the protons from passing through your cells. So what materials do you guys think is better for stopping these protons?